BB84 is a foundational quantum key distribution, or QKD protocol. It was created in 1984 by Charles Bennett and Gilles Bressard, hence the initials of its name. BB84 is often introduced as the foundational success story of quantum security, elegant, mathematically precise, and provably secure. In theory, it shows how the laws of quantum mechanics can be used to detect eavesdropping and guarantee the secrecy of a cryptographic key. But that promise depends entirely on a set of assumptions. Assumptions about devices, measurements, noise, and how information flows through a system. In the theoretical model, quantum states behave ideally, measurements are perfect, and nothing leaks except what the protocol allows. In the real world, those assumptions end. BB84 is not implemented in a vacuum. It is deployed on physical hardware, with imperfect detectors, timing jitter, calibration drift, and noise that doesn't disappear just because the math says it should. The same quantum signals that carry secure information also carry unintended structure, correlations, and leakage. This is where the gap between theory and practice emerges. Not because the protocol is wrong, but because security is not defined by equations alone. It is defined by what survives implementation. In this lecture, we're going to examine BB84 not as an abstract protocol, but as a real system, and understand why a scheme that is provably secure on paper can still fail, quietly and predictably, in practice. BB84 is often described as secure because it makes a very specific promise. If an eavesdropper attempts to observe the quantum channel, their presence will necessarily disturb the transmitted states in a detectable way. This means secrecy does not rely on computational hardness or hidden assumptions about attacker resources, but on the physical behavior of quantum systems themselves. In the idealized model, Alice prepares quantum states, Bob measures them, and any attempt by an adversary to intercept or copy those states introduces errors that reveal the intrusion. From this perspective, security appears absolute, guaranteed by physics rather than probability. But that guarantee is not unconditional. It exists only within a clearly defined set of assumptions that are often treated as background details rather than central requirements. The devices are assumed to behave ideally, detectors are perfectly calibrated, noise is independent and well characterized, and the only information that leaks is the information explicitly accounted for by the protocol. Under those conditions, the mathematics is internally consistent and the security proof holds. The important point is not that BB84's guarantees are wrong, but that they are conditional. The protocol does exactly what it claims to do, but only as long as its assumptions remain true in the physical system where it is deployed. Understanding where those assumptions enter, and how fragile they become outside the theoretical model, is essential to understanding why BB84 can be provably secure in theory while behaving very differently in practice. At a high level, BB84 operates through a simple but carefully structured sequence of steps that combine randomness at both ends of the communication. On the sending side, Alice does not simply transmit bits directly. For each bit, she makes two independent random choices, one for the value of the bit itself and another for the basis in which that bit is encoded. Those bases are mutually incompatible, meaning they cannot be perfectly distinguished at the same time. Alice then sends these quantum states, one at a time, across the quantum channel. On the receiving side, Bob independently makes his own random choice of measurement basis for each incoming quantum state. Because Bob does not know which basis Alice used, some of his measurements align with Alice's choices and others do not. When the bases match, Bob's measurement reproduces Alice's bit correctly. When they don't, the result is effectively random and carries no useful information. After transmission is complete, Alice and Bob communicate over a public classical channel to compare which bases they used without revealing the actual bit values. They discard all the measurements where their bases did not match, keeping only the subset where they did. This process is known as sifting. From the remaining bits, they estimate the error rate, and if it is sufficiently low, they apply classical post-processing steps like error correction and privacy amplification to distill a shared secret key. In the idealized BB84 model, this combination of quantum randomness, incompatible measurements, and classical post-processing is what makes eavesdropping detectable and secrecy provable, at least on paper. In the BB84 protocol, the fundamental reason eavesdropping can be detected is not because an attacker is malicious or aggressive, but because quantum information itself cannot be observed passively. When a quantum state is measured, it is unavoidably disturbed, and that disturbance propagates forward through the system. Any attempt to gain information about the transmitted quantum states, even an attempt that is careful, limited, or partial, introduces subtle changes in the signal that were not present in the ideal transmission. Those changes do not necessarily appear as obvious failures or dramatic corruption. Instead, they manifest statistically as small inconsistencies and errors that accumulate over many transmissions. From Bob's perspective, nothing about an individual measurement necessarily looks suspicious. But when Alice and Bob later compare their results, these disturbances reveal themselves as an elevated error rate relative to what the ideal model predicts. This is the core security intuition behind BB84. Information gain comes at a physical cost. The protocol does not need to identify an attacker or understand their strategy. It only relies on the fact that measurement changes the system, and that those changes leave measurable traces when enough data is examined. In BB84, the system does not respond directly to disturbance itself, because disturbance is not something that can be observed in isolation. Instead, disturbance becomes visible only through measurement, by comparing what was expected to what is actually observed over many transmissions. In the ideal model, when Alice and Bob choose the same basis, the outcomes should align with high consistency, producing a narrow, stable distribution of results. As soon as quantum states are disturbed, whether by noise, imperfect hardware, or an eavesdropper attempting to extract information, that distribution begins to widen. The change is not dramatic, and it is not tied to any single event. Individual measurements still look plausible, and nothing appears obviously broken. But statistically, small inconsistencies accumulate, and the system begins to register deviation from its expected behavior. This deviation is summarized into a single metric that represents how far the observed outcomes drift from the ideal case. At this point, security is no longer about quantum states themselves, but about comparing distributions, estimating error, and deciding whether the observed behavior remains consistent with the assumptions the protocol relies on. BB84 does not detect attacks directly. It detects divergence. And that divergence, once quantified, becomes the basis for every subsequent security decision the system makes. In practical BB84 systems, errors are not a sign of failure. They are a condition for operation. Quantum communication takes place on physical hardware, and physical hardware is never perfectly stable. Sources fluctuate, detectors drift, timing varies, and environmental noise is always present. If a protocol required flawless transmission to function, it would never produce usable keys outside of controlled laboratory conditions. Instead, BB84 defines an acceptable operating region, a bounded range of variation within which the system is assumed to behave consistently with its security model. As long as observed behavior remains inside this region, the protocol proceeds, even though errors are clearly present. Only when measurements move outside that tolerated range does the system classify the behavior as non-operational and halt key generation. This design choice makes BB84 deployable, but it also reframes what security means. Security is no longer the absence of disturbance, but the management of disturbance. Noise is not eliminated, it is accommodated, and the continued operation of the system depends on where observed behavior falls relative to a predefined boundary, not on whether that behavior is perfectly clean. Once a system defines an acceptable operating region, that definition stops being passive. A threshold does not simply separate safe behavior from failure, it actively shapes how the system is used. Any behavior that remains inside the allowed region is permitted by design, even if that behavior carries structure, correlation, or leakage. Over time, this creates an operating envelope, a space where activity is not just tolerated, but implicitly sanctioned. The system does not ask why behavior remains below the threshold. It only verifies that the boundary has not been crossed. As a result, behavior naturally accumulates near that boundary, not because of malfunction, but because the boundary itself defines the limits of acceptable operation. Security decisions become binary at the threshold, even though the underlying behavior is continuous. This means the most informative and impactful activity does not occur above the line, where the system reacts, but just below it, where the system remains silent. In BB84, the threshold is necessary for operation, but it also becomes a guide, signaling exactly how much disturbance is allowed before trust is withdrawn. In BB84, security decisions are made one execution at a time. Each transmission is evaluated independently, and as long as measured behavior stays within the acceptable operating region, the system continues normally. From the protocol's point of view, nothing about any individual run appears problematic. Errors are present, but they remain below the threshold, so the system treats them as noise rather than signal. The important detail is that this evaluation is fundamentally local in time. BB84 assumes that each round is independent, that noise is memoryless, and that nothing meaningful carries over from one execution to the next. But real systems do not operate in isolation. Over time, small deviations repeat, correlations form, and structure emerges across many runs. Even when every individual measurement looks compliant, information can accumulate quietly in the background. The threshold is never crossed, alarms are never triggered, and yet the system's behavior becomes increasingly predictable in aggregate. What is tolerated moment by moment can become informative over time. BB84 remains focused on detecting immediate disturbance, but it has no built-in mechanism to account for slow, cumulative effects that remain consistently below the point of detection. Detection systems are fundamentally reactive. They observe behavior, compare it against predefined rules, and respond only after a boundary has been crossed. That logic assumes that the behavior being observed is static, accidental, or random. But in real systems, behavior does not remain fixed. It adapts. While detection logic stays rigid and binary, observed behavior evolves continuously, adjusting itself in response to what the system tolerates and what it rejects. As long as activity remains below the detection threshold, the system continues to operate normally, regardless of how structured or intentional that activity may be. Over time, this creates an imbalance. The system waits for violations that never arrive, while behavior gradually reshapes itself to fit perfectly within the allowed operating envelope. Detection rules do not anticipate adaptation. They respond to it after the fact. And because the system only reacts when a threshold is crossed, the most informative and persistent behavior is precisely the behavior that never triggers a response. In this way, detection does not fail because it is inaccurate, but because it is always one step behind the processes it is meant to control. Static security models are built on a simplifying assumption that behavior can be evaluated independently, one execution at a time, without memory or adaptation. In this view, the protocol, the channel, and the measurement devices are treated as isolated components, and security is assessed by checking whether each individual run satisfies predefined conditions. That abstraction makes formal analysis possible, but it does not survive contact with real systems operating over time. Deployed systems accumulate state. They exhibit drift, correlation, feedback, and learning effects that cannot be captured by per-execution guarantees. Behavior that appears benign in isolation can become structured in aggregate, and assumptions that hold momentarily erode quietly across repeated interactions. The result is a growing mismatch between what the security model assumes and how the system actually behaves. This is not a failure of the mathematics or the protocol specification. It is a failure of the model to account for time, memory, and adaptation. Once behavior becomes stateful and cumulative, static guarantees lose their ability to constrain outcomes. Security is no longer something that can be established once and assumed indefinitely. It must be evaluated as a dynamic property of a system evolving over time. Security proofs for BB84 are built around a very specific adversary model, one that is deliberately simplified to make formal analysis possible. In this model, the adversary is assumed to be static, meaning their strategy does not change over time. They are memoryless, meaning each interaction is independent and leaves no lasting state. And they are non-adaptive, meaning they do not observe outcomes, learn from feedback, or refine their behavior across repeated executions. This adversary interacts with the protocol once, applies a fixed strategy, and then disappears. Under those assumptions, the mathematics is clean. The bounds are well-defined, and security can be proven rigorously. But it's important to recognize what this model excludes. It excludes persistence. It excludes learning. It excludes long-term observation and strategy refinement. The security guarantee does not fail within this model. It works exactly as intended. The question is not whether BB84 is secure against the adversary it assumes, but whether that adversary resembles anything that actually appears in deployed systems operating over time. In real deployments, the adversary does not resemble the simplified model assumed by security proofs. Instead of acting once and disappearing, real adversaries persist. They observe systems over long periods of time, retain memory across interactions, and adjust their behavior based on feedback. Each interaction becomes a data point. Each response from the system conveys information about what is tolerated, what is corrected, and what remains invisible. Over time, strategies evolve, correlations emerge, and behavior becomes increasingly optimized to operate within the system's accepted boundaries. This adversary does not need to cross thresholds or trigger alarms to be effective. Learning happens below the surface, driven by repeated exposure to system responses and long-term observation of outcomes. From the system's perspective, nothing appears abnormal in any single execution. But, from the adversary's perspective, the system becomes progressively more predictable. This is the fundamental mismatch. BB84 assumes independence between runs, while real adversaries exploit dependence across runs. Once learning and persistence enter the picture, the assumptions that underpin static security guarantees no longer hold, and security must be evaluated as a dynamic process unfolding over time. Security proofs for BB84 rely on a foundational assumption that each execution of the protocol is independent of all others. Each round is treated as a self-contained experiment, unaffected by past interactions and uninfluential on future ones. Under this assumption, errors are modeled as random, memoryless events, and statistical guarantees can be derived by averaging behavior across many trials. But once an adversary is allowed to learn, that independence quietly disappears. Information gained in one execution influences decisions in the next. Correlations form across rounds, even though no single run appears anomalous on its own. What the proof treats as isolated noise becomes structured behavior when viewed over time. The mathematics remains correct within its assumptions, but those assumptions no longer describe the system being observed. Independence is not violated suddenly or dramatically. It erodes gradually as state accumulates. And when executions are no longer independent, averaging no longer provides the guarantees the proof relies on. At that point, the security bound no longer constrains real behavior, not because the protocol was implemented incorrectly, but because the conditions required for the proof no longer exist. When executions are no longer independent, behavior that appears random in isolation begins to exhibit structure over time. In any single run of BB84, small deviations look like noise. They fluctuate, average out, and remain comfortably below the detection threshold. From the system's point of view, nothing appears unusual. But when those same deviations repeat across many executions, patterns begin to form. Peaks align more often than expected. Biases persist longer than random variation would predict, and correlations quietly emerge across runs. What the protocol treats as independent noise becomes statistically informative when observed in aggregate. Crucially, this transformation happens entirely below the point of detection. No threshold is crossed, no alarm is triggered, and every individual execution remains compliant. The system continues operating normally, unaware that the underlying behavior is becoming increasingly structured. Correlation does not require large disturbances or obvious anomalies. It only requires repetition under stable rules. Once behavior becomes correlated across time, predictability replaces randomness, and the assumptions that justified averaging and tolerance no longer hold. In systems that tolerate small deviations, information does not arrive all at once. It accumulates gradually, below the level of detection. Each individual deviation is treated as insignificant, allowed to pass because it falls within the acceptable operating region. From the system's perspective, these events are indistinguishable from noise. But over repeated executions, those tolerated deviations begin to add up. What is negligible in isolation becomes meaningful in aggregate. Small biases persist. Correlations reinforce one another, and structure emerges where randomness was assumed. Importantly, this accumulation does not require alarms to fail or thresholds to be crossed. The system continues to operate normally, confidently applying the same rules that allowed the behavior in the first place. Detection remains silent, not because nothing is happening, but because nothing violates the conditions it is designed to observe. Over time, information is extracted quietly, without triggering any explicit response, and security erodes not through sudden failure, but through steady, lawful operation under tolerance. This depiction makes explicit the fact that security does not fail when a threshold is crossed. It fails when the threshold becomes the definition of safety. As long as behavior remains beneath that line, the system declares everything normal. Detection never triggers. Abort logic never activates, and from the defender's perspective, nothing meaningful is happening. But inside that allowed region, something very real is occurring. Optimization. Each interaction slightly refines understanding. Each exchange reduces uncertainty, and each data point nudges the system closer to predictability. The path you're seeing here is not noisy exploration. It's controlled movement constrained by policy. Over time, that movement becomes smoother, more directed, and more informative, all without ever violating the rules that define secure operation. This is the structural asymmetry at the heart of threshold-based security models. They are designed to react to violations, not to constrain learning. Once an adversary understands where the boundary is, The problem is no longer how to break the system, but how to operate perfectly within it. And because the system itself permits everything below that line, the most effective attacks are not the ones that trip alarms, but the ones that never need to. Here, we can see what the attack surface actually is. We tend to think of attacks as boundary violations, moments where a system is pushed past a limit and something breaks. But in threshold-based security models, the boundary doesn't define danger. It defines permission. Everything below that line is explicitly allowed behavior, and that allowed region becomes the space where interaction, probing, and learning can occur without resistance. Each trajectory you see here represents a legitimate execution path, indistinguishable from normal operation when viewed in isolation. Yet, collectively, they map the system's behavior, reveal structure, and expose constraints. Security, by defining thresholds, is also defining where learning is possible. The more clearly that boundary is understood, the more efficiently an adversary can explore the space beneath it. The paradox is that the system's own safety rules carve out the surface on which it can be studied, optimized against, and eventually anticipated, all without ever triggering detection. Here, we can see the line between observing a problem and preventing one, and that distinction matters more than most security models admit. Detection tells you that something has already happened. It does not stop that thing from happening in the first place. By the time a system reaches a detection decision, by the time statistics are aggregated, thresholds are evaluated, and confidence intervals are computed, the learning phase is already complete. The density you see below the threshold represents information that has already been extracted, structure that has already been inferred, and behavior that has already converged. Nothing here violates policy, nothing triggers an alarm, and nothing appears anomalous in real time. Detection operates retrospectively, asking whether past behavior should have been considered safe, while learning operates prospectively, shaping future behavior long before any judgment is rendered. This is the fundamental asymmetry. Defenders evaluate after the fact, while adaptive processes optimize continuously. A system that relies on detection alone is always late, not because it is poorly designed, but because it is structurally reactive. Security decisions arrive only after the conditions they were meant to prevent have already been satisfied. This view makes explicit a limitation that is often misunderstood, even by people who work closely with security proofs. Proofs do not operate in real time, and they do not constrain behavior as it unfolds. They are retrospective statements about what can be inferred after a process has already completed. By the time a security proof is applied, the interactions have already occurred, the data has already been generated, and the learning dynamics have already converged. What the proof does is evaluate whether, given everything that happened, the outcome satisfies a formal definition of security. It explains the result. It does not shape the process that produced it. The dense structure you see below the threshold represents activity that unfolded entirely within permitted operation long before any proof was invoked. No proof pushes trajectories apart, no theorem disrupts convergence, and no bound prevents accumulation while the system is running. Proofs provide confidence after the fact, not resistance during execution. And that distinction matters because adaptive processes do not wait for validation. They evolve continuously, while formal security claims arrive only once the learning phase is already over. This is not an attack on BB84. It's a clarification of what its security claims actually mean. BB84 is provably secure under a very specific set of assumptions: that the adversary is static, that each round is independent, and that no state carries forward between executions. Under those conditions, the mathematics is sound and the proofs hold. But deployed systems do not live in that model. In practice, behavior adapts, information persists, and each round influences the next. State is carried forward, patterns are learned, and strategies evolve over time. The fracture you see here represents that gap. Not a flaw in the proof, but a mismatch between the world the proof describes and the world the system inhabits. Security is not violated because the math is wrong. It is undermined because the assumptions no longer apply. When learning links rounds together, independence disappears, and the guarantees derived from it dissolve. The key point is simple and uncomfortable. Security holds only if the model matches reality, and when it doesn't, the proof remains correct while the system becomes exposed. Here we see where real-world attacks actually live, not inside the proof and not outside the system, but in the space between them. On one side, security proofs describe an idealized model with static behavior and clean assumptions. On the other, deployed systems operate continuously, carrying state forward and adapting over time. The region in between is where learning happens. It is where calibration is refined, parameters are nudged, timing is shaped, and behavior is optimized, all while remaining within what the system considers normal operation. Nothing in this region violates protocol rules, and nothing here is constrained by the mathematical bounds of the proof, because those bounds were never designed to govern adaptive interaction. This is why adaptive attacks are so effective. They do not challenge the proof directly, and they do not need to break the system overtly. They simply operate in the gap the proof does not cover, learning from normal behavior and exploiting the fact that practice is richer, stateful, and more permissive than the model assumes. Once you recognize this space as active rather than empty, it becomes clear that the most powerful attacks are not violations of security definitions, but behaviors that were never constrained by them in the first place. This brings us to a subtle but critical point. No special action is required for learning to occur. The system does not need to be attacked, interrupted, or stressed for information to leak. Simply by operating normally, it reveals structure. Every pulse sent, every basis choice made, every measurement recorded contributes tiny pieces of information about timing, loss, detector response, and calibration behavior. None of this looks malicious, and none of it violates protocol rules. From the system's perspective, it is doing exactly what it was designed to do. But, from an adaptive observer's perspective, these ordinary interactions form a rich sensing channel. Patterns emerge from repetition. Correlations surface over time, and uncertainty steadily collapses. The learning overlays you see here are not intrusions into the protocol. They are inferences drawn from it. That is why this kind of attack is so difficult to detect and so easy to underestimate. The protocol itself becomes the sensor, not because it is flawed, but because it was never designed to conceal everything its normal operation inevitably reveals. This highlights one of the most important and least intuitive realities of deployed quantum systems. Calibration itself leaks information. To function reliably, the system must continuously adjust timing, detector sensitivity, thresholds, and loss compensation so that it stays stable over time. But those adjustments are not hidden. They are expressed through behavior. Every timing offset, every efficiency imbalance, every dead time response shows up as a consistent pattern in normal operation. Nothing here is secret, and nothing here is abnormal. In fact, the more stable and well-calibrated the system becomes, the more predictable it is. From an adaptive observer's perspective, calibration is not noise. It is a signature. Repeated operation reveals how the hardware responds, how it recovers, and where its tolerances lie. Over time, these responses converge into a clear, structural picture of the system's internal alignment. Stability requires consistency, but consistency reveals structure, and once that structure is learned, it can be anticipated, modeled, and exploited without ever violating protocol rules or triggering alarms. Here is a simple physical truth that security models often try to abstract away. Hardware responds consistently. Under the same conditions, governed by the same physics, real devices behave in repeatable ways. Timing offsets recur. Detector responses align. Efficiencies cluster, and recovery behavior follows the same patterns cycle after cycle. Noise exists, but it rides on top of structure rather than replacing it. What you're seeing here is not an idealized system. It's a real one doing exactly what it was engineered to do. That consistency is what makes calibration possible, but it is also what makes learning inevitable. When responses repeat, uncertainty shrinks. When uncertainty shrinks, behavior becomes predictable. Nothing about this requires interference or protocol violation. It emerges naturally from stable operation. Physics favors repeatability, and repeatability favors inference. Once the hardware settles into a stable regime, every interaction reinforces the same underlying response profile, quietly teaching an observer how the system behaves, not once, but reliably over time. This is what consistency ultimately buys an adaptive observer: prediction. When a system responds the same way under the same conditions, uncertainty does not just decrease, it collapses. Early interactions may feel noisy and ambiguous, but as behavior repeats, patterns sharpen and future responses can be anticipated with increasing confidence. The faint trajectories you see ahead of the signal are not guesses. They are expectations formed from accumulated experience. Nothing here requires interference, and nothing here violates protocol rules. The system is still operating normally, still within specification, still below every defined threshold. But once behavior becomes predictable, surprises disappear. The system stops reacting and starts being read. At that point, observation shifts from passive measurement to foresight, and the difference between watching and knowing begins to vanish. Repeated behavior collapses uncertainty, and when uncertainty collapses, the future stops being random. Here we see where observation quietly becomes influence. Once future behavior can be predicted with confidence, control no longer requires disruption or force. It emerges naturally through alignment. The system is still operating normally, still within every defined threshold, still behaving exactly as it was designed to behave. But now, small and perfectly lawful adjustments can be timed, shaped, and positioned to coincide with what the system is already going to do. These are not commands imposed from outside. They are nudges that accumulate because they are applied at precisely the moments when the system is most responsive. Each individual adjustment is negligible, indistinguishable from noise, and well within specification. Yet, over time, those micro-biases compound, gently steering outcomes without ever triggering detection. This is why control at this level is so difficult to defend against. Nothing is being interfered with, and nothing is being violated. Influence emerges because predictability allows interaction to be synchronized with the system's own dynamics. Once behavior is anticipated rather than reacted to, the system does not need to be pushed. It simply follows the path it was already inclined to take. Here, we see why these attacks are so difficult to see and so easy to dismiss. Our intuition tells us that attacks should look disruptive. Spikes, errors, anomalies, alarms. But adaptive attacks don't behave that way. They remain fully within specification, stay below every defined threshold, and operate entirely inside what the system considers normal. The flow you're seeing here is smooth, compliant, and boring by design. Logs look clean. Metrics look healthy. Nothing appears broken or out of bounds. Yet influence is already present, woven into ordinary operation. This is the dangerous inversion. The more carefully an attack conforms to expected behavior, the less likely it is to be detected. Defenses are tuned to spot violations, not conformity. When learning, prediction, and control are embedded inside nominal operation, there is nothing obvious to flag. The system is doing exactly what it was designed to do, and that is precisely why the attack works. Here we see the final alignment of everything that came before. BB84 is not broken, and its mathematics are not wrong. The protocol does exactly what it was designed to do under the assumptions it requires. Those assumptions include independence between rounds, memoryless behavior, and a static adversary that does not adapt over time. In that world, security holds, but the environment BB84 now operates in is fundamentally different. Modern systems persist, state, recalibrate continuously, and interact repeatedly with the same hardware under stable physical conditions. Learning emerges naturally from that repetition. Structure accumulates, predictions form, and influence becomes possible, all without violating protocol rules or triggering alarms. This is not a failure of cryptography. It is a mismatch between an idealized model and a learning reality. The protocol assumes a world that no longer exists, while deployment lives in one shaped by adaptation, memory, and inference. When those two worlds diverge, the proof remains correct, but the guarantees no longer describe what is actually happening. Security still holds, but only under the assumptions the protocol was built for. To wrap this up, BB84 remains a foundational and mathematically sound protocol, but its guarantees are conditional, not universal. In modern deployments, systems operate continuously, hardware behaves consistently, and interactions repeat in ways that allow learning to occur below detection thresholds. Calibration, stability, and normal operation all reveal structure over time, enabling prediction and eventually influence without ever violating protocol rules. These behaviors do not look like attacks, and that is precisely why they are so effective. The challenge is not that the cryptography is wrong, but that the adversary model has changed. BB84 was designed for a world without adaptive, learning adversaries, and today's reality no longer matches that assumption. Understanding this gap is the first step toward building quantum systems that are secure not just in theory, but in practice. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.